Okay. All this time we have been looking at how to get a high gain for the op amp, right? And we kind of started off with a common source, converted to the 5 transistor OTA, and then made the cascode. And here also we saw we can make the telescopic cascode, folded cascode. And in the last class I also showed you a technique to further boost the output resistance, which I showed it for a telescopic cascode, but you can also use it for the folded cascode. Okay, but now you seem to know a lot of techniques for getting a high gain, but unfortunately that's not the end of the story. There are more problems to tackle, and it's a good thing to have problems because you'll have jobs, right? And yeah, so one of the problems is that, let's say I make this OTA, and of course if I try to measure this gain, I'll apply a sinusoid of small amplitude and measure how much it gets amplified here. If I keep doing this experiment across frequencies and I measure what is the gain I get, how do you think it will look like? I'm saying, let's say I try to measure the gain at starting from low to high frequencies. Everyone is convinced that at high frequencies it should drop, right? How it drops, that's something we don't know yet, but at least it makes sense that it should drop. And why is that? Right? Because the MOSFET, although it looks quite simple like this, has intrinsic capacitors across each of these terminals, right? And as one of you pointed out, we also have a bulk terminal, which for the NMOS is usually grounded in most of the CMOS processes. So you'll also have capacitors from drain to bulk and source to bulk, right? So it is not such a simple looking device at all. So because of this, you will see the gain will drop at high frequencies. So we'll try to see how it drops. And as usual, we'll start with simple single transistor stages, derive it completely, get some intuition, and based on that understanding, we'll try to qualitatively estimate the poles and zeros for more complex structures. Okay, so let's start with the simple common drain. So in common drain, I'll apply the input at the gate, take the output at the source. See, drain is at VDD. I have a current source here. So finally, when I replace this current source by a transistor, what transistor I'll use? NMOS. So let me replace it now itself. So let's say this is M1 and M2. Okay, so let me quickly draw the small signal equivalent for this. I'll have the input connected to the gate of the first transistor. I'll have the GM VGS and R0, and the drain is incrementally grounded, right? So this is R0 of the transistor M1, and this is basically connected to some bias voltage for M2. So how does M2 behave in small signal? It's not a short, right? It just only has an R0, right? R02. So, okay, great. So now let's quickly add capacitors here. So we'll have a capacitor from the gate to the source for the transistor M1. We'll have one from gate to the drain. We'll have one from the drain to the bulk. We'll have one from the source to the bulk. Bulk is a substrate, body terminal, right? That's usually called the bulk, substrate, body, whatever. Okay. So now let's look at M2. M2 gate and source and the body are all incrementally grounded. So what is the only capacitor it will have? Between drain to bulk. Okay. And basically that will also get added here. Okay. So now if you look at the capacitors we have marked, so this capacitor here is connected from ground to ground, so it's not relevant, right? So this capacitor, if you see, it is connected, one end is connected to the voltage source, other end is ground, right? So this capacitor is basically across a voltage source. It doesn't play a role at all, because the voltage source is going to fix that voltage irrespective of what the capacitor is. So this is also not relevant to us, and these two can be lumped together as a single capacitor. So if I had to simplify it, I'll have this guy. I'll just have a capacitor from gate to source. I'll have the GM-VGS, this is ground. And also if you look at R01, it is connected from this node here to ground, right? And same is the case with R02. So I'll basically combine the two in parallel, and I'll call it as some R0, which is R01 parallel R02, and of course you have the final capacitor here. Okay, so let me label these capacitors C1, C2. Okay, I mean, you guys know what C2 is. It consists of drain to bulk, whatever. That's not the point of this course. We know that we have capacitors here. We'll see how they are going to impact us. Okay, great. So this is basically GM1 times VGS. If I call this VA and Vout, what is VGS? This is the gate, this is source, right? What is the VGS? In minus Vout. Okay. So yeah, so why don't you guys work out and tell me what will be the ratio Vout by Vn? And of course we'll do it in the Laplace domain, right? Because you have capacitors, Laplace domain converts differential equations to polynomials, and we are more comfortable dealing with algebra and polynomials we learnt in 6th standard than derivatives we learnt later. So work out and tell me what this is. Okay, I forgot the number, maybe 9, I think. One is responding. What is it?
GM1 plus SC2 plus G0.
Sorry, GM1?
Upon GM1 plus SC2
Okay.
plus G0.
I believe something is missing here. Plus SC1. And then? Is that all or something else is there? Here you should have one more SC1. So what I've written is fine? Okay. I mean, R0 is basically this G0. 1 by G0. I think that's what you meant, right? Someone told G0. G0 you meant 1 by R0, right? Okay. So anyways, okay, I think this is I mean, you have only one node here, you apply the KCL and you should be able to get this. And I think this is the right expression. Okay, so let me actually take it to next page. Okay, great. Right, okay, so usually the transfer function we write in a standard form, which is of this form, n0 times 1 plus S by Z1 times. Similarly, at the denominator, we separate out the poles and write. Okay. I mean, the reason is simple. I mean, here it's straightforward that what is A0 here? DC, that is, if I put S equal to 0, the gain evaluated at DC, right? So this directly gives the gain we have computed all this time without the capacitor, right? So if you write it in that form, what you get, I'll have GM1 by GM1 plus G0 times 1 plus SC1 by GM1 C1 plus SC2. Okay. So what is the DC gain we get? It's GM1 by plus G0. I mean, you can, if you put G0 as 1 by R0, you will get the same old expression that we are familiar with. Okay. Same thing, right? When we had a resistor R0 at the source, this is the gain you get for the common drain. And in addition, now we also have a pole and a 0. Where is the pole located at? Huh? Pole is the denominator, right? So what is it? G0 by 2. What about the 0? It's minus GM1 by C1. Okay, that's also important. Okay. So okay, let's see why these pole locations and 0 location make sense. So hopefully you guys might be aware that poles are basically a characteristic of a particular system or a circuit, and it does not depend on where you apply the input or where you take the output. It is sort of the natural behavior of the system. So it's basically independent of where you apply the input and where you take the output from, right? So let me copy paste this guy. Yeah, so here let me get rid of this. So to get an estimate of the pole location, I don't have to apply the input because it doesn't depend on the input. So I'll just ground this, right? And now when I do that, V in goes to 0. So here this just becomes minus GMV out. So I can redraw the circuit as GMV plus GMV out flowing up, right? So let me quickly do that. This is GM1 times V out. Okay. So now you see you have only one node here. And what is the capacitance at that node? Total capacitance? C1 plus C2, right? So you have total capacitance of C1 plus C2. And what is the total resistance you have? You have this guy R0. And if you look at this fellow, the voltage is V out. It takes in a current of GM1 V out. So this is basically 1 by GM. So this is R0 parallel 1 by GM1, or in terms of the conductance, it's basically G0 plus GM1. Okay, and that's why the pole location we got was this GM1 plus G0. Okay, great. So okay, let me ask this then. Now you see that I have two capacitors here, but I have only one pole. Why is that so? Huh? Yeah. Yeah, I mean, okay. Yeah, that's the deal. See, it turns out that without going into a lot of details, the number of poles you have depends on the number of independent state variables or the degrees of freedom. And if you were to, like relate to thermodynamics, it's the number of degrees of freedom. And in circuits, the state variables are basically those that has memory. And in circuits, what elements have memory? Right? It's now simply capacitor voltages or the inductor currents. And here we'll only deal with capacitor. So whatever is the number of independent capacitor voltages you can set in the circuit, that determines the number of poles, right? And here, if I set this guy's voltage, the voltage of C1 is also set. So you don't have two independent choices, you just have one.
So did you write the code directly by G by C?
Yeah. I mean, you just have the point is you have an R and a C finally, isn't it? So the pole will be 1 by RC. In this case, you can write it. I mean, of course, like he's saying, this trick you can't apply to everywhere. Like for example, if you have more complicated network, or I mean, simply speaking, just looking at the capacitance at a node, resistance at the node, and taking the 1 by RC, that will give us something. But whether it will be the exact pole, that is questionable. And also, this when you do this, right, we can only get real poles, isn't it? But poles can be complex. So in some cases you can do, and in these simple cases this works out. So we'll deal with, we'll look at this in detail more later, but as of now we just have one R and one C, so the pole is 1 by RC. Okay, and the number of poles, as I mentioned, is the number of independent capacitor voltages you can have in the circuit. Great. So now let's look at zeros. So you know that at 0 what happens to the transfer function? What happens? As the name suggests, it will go to 0. It went to 0. So at 0 the transfer function basically goes to 0. I'm really sorry, I'll have to write it again. So which means the output V out of S, that will be 0 for any input. Okay, right? And say you have a quantity V naught of S to be some V of S, right? So what is the simplest linear operation you can do to get this quantity go to 0? Okay, that is okay. Let's not go to infinity. I mean, it's much more simpler. I mean, what is the simplest operation you can do to this guy so that this becomes 0? Minus the same thing, right? I mean, that's all. I have 3 chocolates given to you. Someone takes it out, it's 0. As simple as that. So it's, if I do this guy, 0, right? So this is exactly one way in which 0 happens in a network. The other way is that you can have currents of opposite phases that might flow into an impedance and generate a 0 voltage. Okay. So basically there are 2 ways in which you can have a 0. Not the only ways, but usually this is how it happens. So in the first way, you will have the final voltage to be sum of different voltages, and all these different voltages must have different phase shifts. Only then it will add to 0. I'll just say different phase. So here in the second case, you will have a 0 when you have multiple paths for the current to flow from input to output, and those currents will be of opposite phases. So multiple paths for current, say from input to output, different phases. Okay. So if you understand this, let's play some games. So let us say I have a simple network like this. Say this is say R, C1, C2. And by the way, do you think the location of 0 will depend on the input and output locations or no? Why? I mean, poles are a system property. See, to get a 0, what we are doing essentially, we are finding some output and you can add a path from the input to the output with an opposite polarity to cancel it. Okay. So it does depend on where you apply the input and where you take the output. I mean, for example, this cancellation might happen for 1 voltage in a circuit. If you look at some other voltage, you can't guarantee that this will happen, right? Does it make sense? So this indeed actually depends on where I apply the input and where I take the output from. Okay. So when I give a network and ask if this has zeros, what should be the first question you should ask them?
What is the input and output?
That's all. So this is the input. So here let's say I call this as the output. So from the understanding we have so far, do you think this has a zero? I mean, we know two ways in which zeros can happen. First is when you have output voltage obtained as sum of some voltages. So here this is the voltage. It's not obtained as sum of some voltages. Number two is when you have multiple paths from the input to the output, and currents can flow in these two paths, and those paths must have different phases. Do you have something like that here?
Yes, sir.
We do have, right? So we have current here and here. So there is a zero here. There could be a zero, right? And it turns out there is a zero here, and a simple way to find the zero location is, well, you know that, let me get rid of this guy, yeah, zero is there. You know that at 0, what can you say about V naught of S? 0. So one simple thing you can do is I will apply KCL at the output node at that 0 frequency. So here I know that this voltage is 0. So what is this current? Huh? That's also 0. So now we can add up these two currents and make it 0. So what are the currents?
V1 by R, V1.
So Vin of S into SC1 plus Vin of S by R 0. So if I simplify this, I'll have to be 0. Of course, for this to be valid, either this guy has to be 0 or this guy. And of course, we are not applying 0 input. So the second term here must be 0. So which means what is the 0 location? 0. And this in turn is the 0 location. You can work out and check if you want. Okay, so let me show you one other example. Okay, so here I apply the input at this point and take the output here. R2 and C. Okay. So again, I'm defining the output as the output of this node. So do you think there is a 0 here or no? Output is obtained as a sum of two different voltages, and these two voltages have different phases, right? Because one is a capacitor voltage, one is a resistor voltage, and this indeed has a 0. So again, to find it, you can just do KCL, right? So I have, let us say, I of S. So basically what happens is I of S flows into R2 plus 1 by SC to give you 0, isn't it? I mean, this is the sum of the two voltages. Okay. So what is the 0 location now? I mean, of course, this guy is not 0 because I of S is V in by R, right? Because remember, this is 0, which means the current I of S is V in by R1. That is not 0. But this non-zero current flows through this impedance to generate a 0 voltage. So which means the second term in the bracket is what is 0. So what is the value of S then? To C. Okay. Fine. So let us say I take the same network and define that I am going to take the output here. So now is there a 0? No, right? Because I mean, the output is taken as the capacitor voltage, so there seems to be no possibility, and it should be, I mean, it should be obvious to you guys because yeah, this is basically your simple RC circuit, right? I just split this single resistor as 2, that's all. Okay. So, I mean, by this you should understand that the 0 actually depends on where you take the output also. Okay. So,
Level circuit. You said the poles doesn't depend on the output. But
poles, yeah, correct.
output, inputs are understood, but output also doesn't.
It doesn't depend.
But it will depend if you took the output at the yellow dot or the between R2 and C.
Right. You can work it out and check. You can work out and check, right? You can check. Poles will not change.
So when you say that it doesn't depend on the output and input, does it mean that position also?
That's what I mean. Yeah. Position of, when I mean it doesn't depend on the input and output, I mean where I apply the input and where I take the output, not the values of them. I mean, if you have taken some controls, you'll know it's basically the characteristic equation. I mean, I don't know, you might SI minus A something. So it doesn't depend on the input matrix. I don't know if you have taken controls course, but anyways, yeah. Okay, so actually let me also explain you one other trick, which is actually a more foolproof way to determine if you have a 0 or not. And to explain that method, let me take a example transfer function. I'll assume that it has 1, 0 and 3 poles. Okay. I mean, this is an example transfer function, but you can actually prove it for any general network. So here I have 3 poles, so I'll have at least 3 capacitors. Okay. So now, if you think about it, in the transfer function I have the term S due to which element in the network? Capacitors or inductors, right? Here I have only capacitors because admittance of the capacitor is S times C. So the S term will always come with the capacitor. Is that fine? So if that point is clear, I will expand this like this. So I'll have S times C1 times some resistor. This could be the way in which I can get the S term in the numerator. Okay? Is that okay? Huh? What I'm saying is the S term comes along with the capacitor always. So along with S term I have written a capacitor, and that could be 1, 2 or all of them, right? Similarly, the denominator I'll do the same thing. I'll have S, so that could be C1 times some other resistor RA, C2 times some other resistor RB, RC. Okay. So what will generate the S square terms? It will be the product of capacitors. So I'll have C1, C2 times something, What about the S cube? It will be the product of the 3 capacitors, that's all. Right? This is how the transfer function will finally look like. And by the way, so can I have a C1 square term here? Why not? Huh? I mean, it seems, I mean, it's product of capacitors, so why can't I have the self capacitor multiplied by itself? Huh? Okay, so again, these things you can prove by contradiction. So say you have, I put C2 and C3 to be 0 in the network. How many capacitors will I have then? So what is the order of the system? It's a first order system. Okay, but if you have a case where this guy is also present, if you put C2, C3, 0, so these two terms go away, but you'll have an S square, C1 square term also, right? So which means you can't have a C1 square term, or for that matter any capacitor power, taken to a higher power. Okay, so in transfer functions you can never have some Ci power m where m is greater than 1. If you have products, it will be product with some other capacitor, but not the same capacitor. Okay, so now let's get back to the discussion. So, see, this is the transfer function. This term is not there. Now let us say here I tend C1 to infinity. What will happen to h of s? Will it be 0 or non-zero? Huh? If I tend C1 to infinity, okay, only this term will dominate in the numerator. In the denominator, again, only the C1 terms will be dominating. Right? And in all of them, I have C1 in common. So C1 cancels out. So will it be 0 or non-zero? Is that okay? Simple limit. So h of s will be non-zero. I mean, this is also true if you tend any capacitor to infinity, right? Okay. So this is true. And remember, in this case, I have a 0 in the system. Okay, so this we know is true if h of s has a 0. Now let us say h of s is, does not have a 0. So which means I will not have these terms, right? So now if I do the same thing, what will happen to h of s? 0. Okay. So now can you suggest a technique in which I can determine if I have a 0 or not? Right? You take each and every capacitor, tend it to infinity, and see what happens to the output. If the output is not 0, then you have a 0. Okay? So that's what we see, right? If the output is not 0, then you have a 0. Fine? And doing this, sorry?
What if two capacitors have the same value?
Doesn't matter, its values are immaterial, right? You have two independent capacitors. What's your question actually?
So if
Oh yes, C1 square term. Huh? Oh, that's a different case, right? You are saying C1 square term. That is a special case where you have two separate capacitors with equal value, then the number squares.
so this will hold true like having a 0 also will hold true when HS tends to 0.
Right.
This will also hold when C1, C2 and C3 are distinct.
I have not made any assumptions, right? I have taken C1, C2, C3 to be unique. Even if they are equal, it should be valid.
So we started with that if C1 tends to infinity.
Correct.
We'll get some finite value.
Right.
And so if C1 and C2 are equal,
Okay.
then we'll have a term of C1 square in the denominator.
See, I mean, that's a particular value, right? We'll not deal with values, right? Okay. I mean, so this point is clear. So the technique is you take each and every capacitor, make it infinite, see if the output is not 0. If the output is not 0, you have a 0 in the network. Okay. And I mean, this technique will tell you if you have S term in the numerator. So it turns out if you want to know if the network has two zeros, logically what do you think we'll have to do? To find if I have 1 0, I am taking, that's all. So what I'll do is, for finding if I have 1 0, I am taking one capacitor separately and putting to infinity and checking. If it has two zeros, you can argue the same way. You'll have to take two caps at a time and simultaneously tend it to infinity. Okay. So the takeaway is foolproof way of finding if you have a 0 or not is to take each capacitor, tend to infinity. If the output is not 0, then you have 0. Okay. And we also saw a slightly more intuitive way to find if you have zeros or not, which is to observe if the output voltage is sum of some voltages, with different phases, or you see if you have multiple paths from the input to the output, multiple paths for the current, okay, and the paths must have different phases, right? So I am saying this is a more foolproof technique is, say you have this network, okay, again C and R. So now do you think it has a 0 or does not have a 0? I mean, at least here it doesn't look like output is sum of voltages. There are no multiple paths. But let's take this proper route. I'll turn this capacitor to infinity. If I make a capacitor infinity, what happens? It's a short circuit, 1 by so is the output 0 or non-zero? Output is non-zero. So you indeed have a 0 here. Okay. And does anyone know what the transfer function is? I mean, look, we can quickly find it. So this is the input C and R. What is the transfer function? Right? So you indeed have a 0 at s equal to 0. Okay. So I mean, basically this technique tells you if you have a 0 or not. Existence of 0. And if you want to find the location of 0, you do the same thing. You apply KCL at the output. Okay. And then find it. So let me just finally finish our source follower. So now we have our source follower, the common drain case. So do you think this has a 0 or does not have a 0?
Yes.
So if you see that if I short this cap, the output is 0. But if I short this guy, is the output 0 or non-zero? So we have a 0, and logically also it should make sense because you have two paths for the current to flow, and again to find the 0 location I will take V out to be 0, right? I will apply KCL. So what is the current flowing here? This will be 0. So the only currents flowing are these two fellows. What are the currents? Can you quickly tell me? We will finish off. VI
into S1
plus V in. Okay, this should be 0. So which is possible if S is, and that's the 0 location we also got. Okay. So any doubt? Okay, so we'll stop here and he'll continue.